First, just a few things about the last exam, since we're going to have another exam on Friday. Yeah, hooray, good times. I did go through and looked at the questions. I'm going to show here the ones that were most commonly missed and what the situation was. I also corrected the problem 20 that had 2 correct answers. So that should all be graded correctly. And I updated the score. So let's just go over these questions that people scored poorly on. So the first 3 are the ones that people did the worst on. Question number 1, which of the beams is due to alpha particles? Now, I'm not going to ask you to answer A, B, C. What I'm going to do is to lead you to the thought process that this was shooting for. So what can you tell me about alpha particles? They're what? They're the easiest to stop. True statement. It's not going to help me answer this, but it's a true statement. They're positive. That's the statement that's going to help me solve this, right? So we have this particle, and to figure out the answer, we have to identify which portion is going to be useful to me. Why is the charge useful to me? Because I have the particles are all passing through charged plates. That's what tells me the charge is going to be important. So the thought process of why the charge is the important aspect comes from, I have a picture that has them passing between charged plates. Now, if it's a positive charge, is positive charge attracted or repelled or neither from positive? Positive and positive repel. So that means it's going to have a force that pushes it away from positive, and of course it's attracted to negative, so toward negative. So which particle here, A, B, or C, is being repelled from positive and attracted to negative? C. And so that's how you got your answer. Or that was the thought process, I should say. That's what it was looking for. Everybody understand the thought process involved here? Because that's the real physics, is to look at something and figure out what are the important pieces and how do they fit. Okay, the next one. In order for a chemical reaction to be balanced, it has to have blank on each side of the reaction. This is, of course, a student, actually, of the ones that did the poorest on. The student ones were all but this, or were only this one. All the rest were textbook ones. In order for a chemical reaction to be balanced, it has to have what is the same on both sides? Same amount of each element. Okay, same amount of each element. And if it has the same amount of each element, since the elements all have a fixed mass, it's also going to have the same mass. So the correct answer was D, because by virtue of having the same amount of each element, it has to have the same mass as well. So I imagine, I didn't look at this one specifically to see the breakdown, but I imagine that most people probably simply said the same amount of each element and didn't make the further connection on mass. Which of the following is most easily understood to be quantized? What does that word quantized mean? Fair enough. Quantized means that it comes in chunks. That is, you can have one of these, two of these, three of these, but you can't have 1.675 of these. And so when you look at this, you're just saying, which one comes in chunks? The amount of air in a balloon, is there only, I could have this amount of air or this amount of air in the balloon? No, so that's not correct, because you could have pretty much continuous amounts of air. I say pretty much. It is 1 molecule, 2 molecules, 3 molecules, but it's not easily understood that way because the molecules are, there's so many molecules in the balloon that we think of it as just continuous. So that's why it has the words easily understood, because technically it would be quantized, but it's not easily understood as quantized. The amount of water in a glass. Can you only have, 1/4 full, 2/4 full, 3/4 full? No, it can be, once again, continuous with the same, technically it's one molecule at a time, but there's so many molecules that we think of it as continuous. The amount of time in an hour. Is there only this amount of time in an hour, this amount of time in an hour? This one's a little more confusing, right? What it should say to make it less confusing, amount of time, let's say a job takes. Jobs can take more or less time, but it's a continuous amount of time. You could have it take, a fraction of a second more, 2 minutes more, any amount more or less. So it's, once again, not quantized. Number of eggs in a carton. You have individual number of eggs, or can you have a continuous number? We're down to it's either D or E. What do you say? My ears could not differentiate between if you said D or E. D is correct, because you'd have 1 egg, 2 egg, 3 egg, 4 egg. You're not going to have 1.625 eggs in the carton. And so that is the most easily understood as quantized. Now, number 14 is probably the poorest worded of all of these questions. How is it possible to deduce the identity of an element from its electron configuration? I will go to the correct answer and then look at the other ones. The correct answer is, if the atom is electrically neutral, then it has the same number of electrons as it has protons in the nucleus. And if you know how many protons you have, then you know what the atom is exactly. Well, you know what element it is exactly. Right? You don't know what isotope it is, actually. So that one there, if you have that information, the number of electrons corresponds to its atomic number, so you know what element it is. That was the correct answer. But if you look at the other answers, the first one, an electron configuration is unique to each element, much like its atomic spectrum. Well, if in your mind you said, you added the words neutral, well, that's one word, neutral. If you said the electron configuration is unique to each neutral element, that actually would have been correct. And so if in your mind you didn't think about, well, you could add an electron or take one away, you would have come to the same thing. There's also a further aspect to this that you could think of. The energy levels, it says in there, the atomic spectrum. The atomic spectrum is the result of the differences in the gaps. And so the atomic spectrum is exactly reflecting the electron configuration. And the fact is, if I have a fluorine atom that is neutral and an oxygen atom that has one extra electron, so they both have the same number of electrons, the truthful electron configuration is a little bit different because you have a different number of charges in the nucleus, making the forces different. So there could be further wiggling on that to make A more correct. So that's why I said this one here is the poorest worded of the problems, because I could see somebody championing this one and taking it to the nitty-gritty and saying A has to be considered correct. B, using the periodic table, the outermost occupied shell indicates the group, while the number of occupied shells indicates the period. For the most part, roughly correct. Not exactly correct, but for the most part, roughly correct. But once again, it doesn't say for neutral, and so you'd have that implied neutral. The reason I said roughly correct is because, if you go down to, well, the filling, your first column is indeed following the shell. But then by the time you get to the third column, you're off by a few rows on the shell. And finally, C we could rule out. C was the only one that you could never argue for. Final one of these questions, according to the following reaction, which molecule is acting as an acid? What was the mnemonic that I told you should memorize? Bases? Okay, so bases, accept. Acids, donate. Okay, so what we're looking at here, which molecule is acting as an acid? So which one is donating? And what's it donating? Proton. So it's asking which one is donating a proton. So by virtue of the arrow going to the right, the one that's donating the proton has to be something that's on the left-hand side. If the arrow is going the opposite direction, then we consider the ones on the right. So my answer is going to have to be either, well, one of the first two. And then we say, okay, which one's donating a proton? That means it has one less hydrogen on the right side than it had on the left side. This one has one less hydrogen. So that means that the one that donated it was this here. And so that there was sulfuric acid. If the arrow had been going the opposite direction, which one would be acting as an acid? The hydronium, the H3O+. Now, how many questions did I go over here? It's not a hard question. 5 of them. And so what I did is I graded the test out of 45. I basically said, some of you got these bottom 2 right, but I just gave everybody out of 5 less points. So after regrading, fixing the one problem 20, the top score is then 40 out of 45, which is still only 90%, not as high as I want. I'm guessing not as high as you want as well. Just going out on a limb there. But that's what I've recorded. Any questions about that test before we go on to today's talk? All right, just want to make sure I gave you plenty of time. We're going to talk about geologic time today. Now, that's a big topic. Might have a little overflow into our review on Wednesday, especially because I spent 15 minutes going over the exam. Geologic time is looking at what's happened in the past based on what we see buried in rocks, the fossils that we see in rocks. So, scientific understanding of time. Scientific understanding of time is different than what Usher's chronology says about time. How many of you are familiar with Usher's chronology? Only one. So in brief, Bishop Usher wrote his series of books, I think it's Annals of the Earth. It's something like 23 volumes. It's a big thing. And what Bishop Usher did was he looked in the Bible and other secular documents to try to determine what the true timeline of the earth is. And he said, well, the beginning of the Bible, we have genealogies. We have Adam lived this long and he begat his third son, Seth, and then he lived this many more years. And then Seth lived this long and he begat Enosh, and then he lived so many more years. And Enosh lived this long. And so we have those genealogies that give a time that each person lived before the son or daughter of record was born. I say or daughter. There are a few women mentioned in the genealogies, although they don't lead you to a time. So he goes to those genealogies, and then that takes you to the flood. you have the flood, and after the flood, you have events. So long between this event and that event. So long between this event and that event. So he puts these all together, genealogies in the Bible and the events in the Bible, and then correlates to other historical records to come to an age from the beginning of the numbering of Adam's day until the present. And Bishop Ussher's work gives you around 6,000 years. So most of us, I'm sure, were raised with the biblical understanding that the earth is probably around 6,000 years old. So that now Bishop Ussher's work is really quite good. There are little things to quibble about. Scientists don't agree with that at all. This being a science class, I want you to be aware of what the scientists believe. There are reasons for believing differently. Number one, they start with the worldview that there are no miracles. That everything that has ever occurred on earth occurs just because of the laws that, well, I say the laws that God created. They would say the laws of nature that just exist. So no miracles. Hence, they're not going to take anything that the Bible says, the Bible being a book talking about a miraculous creator, with any validity. Instead, they're just going to go with what they get from human reasoning. And they use radiometric dating as a primary dating tool, not the only one, but a primary dating tool, to give them the age of the earth around 4.5 billion years old. I usually just round that to say 5 billion years old. So that's the scientist's belief for the age of the earth. And so if you were to take 1 year on earth and try to map the entire earth's history on it, so that the formation of rock, the very beginning of the earth, is January 1. The oldest rocks that exist today are about the end of February. So the first 1/6 of the earth's lifetime, according to science, we have no record of it. But we have rocks that still exist from about 1/6 of its age. The first bacterial life, and this is a highly conjectured bacterial life, basically they find what looks like little bubbles in old rocks, and they say that must have been bacteria, right? It's not really a strong way of saying it was bacteria. Would come a month later, so about 1/4 of the Earth's history there. Then we get to dinosaurs. Dinosaurs would have occurred within the last 2 weeks of the year. And of course, we think of dinosaurs as way in the distant past, because it is way in the distant past. But compared to the time scale, very recent. Homo sapiens and Homo sapiens sapiens, that's us, are things at the very, very, very end of the year. So they're very recent. So when we talk about human history from a scientific perspective, human history is a very brief amount of time. On the other hand, from a biblical perspective, if you're going to take Ussher's chronology, then all of the Earth's history is human history. There is an intermediate ground. I actually believe that the universe and the rock, the Earth, is something on the order of this old, but that God did create life on the earth as described in the Bible at a time separate from when he created the universe. And so I put a difference between the age of the earth and the age of life on earth. But that's a personal interpretation, a personal reading. I'm not here to indoctrinate you. I'm not here to tell you you have to believe the scientific ages. But what I am here to say is you at least need to understand what they are. You don't have to have these memorized as we go through. You don't have to say, oh yes, we have the Cambrian. Then we have, you don't have to have the order. You don't have to have the dates. You don't have to say, so the Cambrian ended 542 million years ago? You don't have to have that memorized. But you do need to know the basics of what's going on, why scientists believe that the earth is this old and what the sequence is. So here is a picture of the Earth's history that I really kind of like. This is just showing it as a circle. And in the circle, it has GA. GA does not stand for Georgia. it stands for giga ages. Giga ages. I said giga like I was, Back to the Future. Giga means billion. So 4.6 giga ages is 4.6 billion, and an age is a term for a year. So 4.6 billion years ago is the beginning of Earth, according to this. Up at the top says 4.55. That 4.55 is rounded to 4.6. M is mega, so mega ages, million years. So that's where we have the formation of the Earth. These things here are referring to the end part. Those are not at the beginning. Those are the end. And so we have the Hadean. What does Hadean make you think of? Makes me think of Hades, because that's what it means. The Hadean period is the period that was like hell. Earth was like hell. What is hell like? Well, traditional view is hell is molten, fire and brimstone. And so that's when the Earth was a molten ball of melted rock. Not a lot of life possible on a molten rock. So the Hadean would be no life, period. The first life then occurs here at about 4 billion years ago, the beginning of the Archean. If you say Archean, that sounds kind of like archaeology. And what is archaeology? Because it is the same root. What is archaeology? Study of what? Okay, artifacts. I thought you said art, and I was like, well, yeah, studying artifacts that are archaic, which means old. So this Archean period is the very old. It's good that we have at least words that make sense. And then you get up here to the Proterozoic. Is it not Zoic? Proterozoic. The Proterozoic is when you can start to have life forms. The Proterozoic is when you start having things that they think are bacteria and developing into, by the end of the Proterozoic, you have trilobites, little things that live in the ocean, little bugs, if you will, that live in the ocean. And so you look here at these lines. I got to zoom out a little so we can see it. The purple line is prokaryotes. Those are your most basic single-celled life forms. So the belief here is the prokaryotes started about 4 billion years ago. And then you have your next life forms, the eukaryotes. Those are cells that, I'm not a biologist. I believe eukaryotes are cells that have a mitochondria in them. And what?
They're like animal cells.
Okay, and like animal cells. So that begins somewhere here around 2.2 to 2.3 billion years ago, according to this. And then we have multicellular life somewhere around 1.6 billion years ago. Finally, you get to what we call animals here at somewhere around, let's say, 750 million years ago. So the first things that we would consider animals 750 million years ago, according to the scientific understanding. And then we get to that 542 million years ago. The 542 million years ago is when we go from the Precambrian to the Cambrian. That's when you have the explosion of life. So it has marked here the Cambrian the Cambrian explosion. You have suddenly lots of different life appearing. And we get to land animals, mammals, hominins. We are hominins. And then you see the hominins occurring right here at the very, very end. That was December 31, 1150 on our 1 year calendar for the first hominins. And then humans was at 11:59 p.m. for the first humans. So the first hominins, the first human-like species are believed to be 2 million years ago. So that is the timeline according to evolution. We're going to spend more, or evolution, according to science. We're going to spend more time looking at these along the way. How do they get this? First, uniformitarianism is a really important piece of the scientific interpretation. The scientific interpretation says that the processes of geology that have occurred in the past are the same processes that occur today. Now, of course, you don't have the same process in a swampy environment as you have in a desert environment. But the types that you have are going to match what the local conditions are and should be the same types that we have for those conditions today. So uniformitarianism says that we've had a uniform set of processes that have occurred throughout time to explain all of what we see when we dig up old rock. When we look at an outcropping, we see, oh, here's this layer, here's this layer. We're saying, well, these layers were formed by things that we see today. And there is superposition. I don't know if I have a separate slide on superposition or not. Yeah, I do. Next slide. So superposition, I'm going to go to this one and then come back. Original horizontality, those are two important concepts related to the laying down of the record. Original horizontality says that sedimentation almost always occurs when you have water go from fast to slow. And when it goes from fast to slow, you're in a still body of water, usually, and that still body of water probably is going to have a pretty close to horizontal floor. So you're going to put sediment layers pretty close to horizontally down. So that's what original horizontality means, that the original layers were horizontal. When we look at them, you might see an outcropping as you drive down the freeway that's at a very steep angle. Well, how is it going to be at a very steep angle if original horizontality is true? How does it go from this to this? What? Erosion? Erosion will bring things down, but that doesn't account for the tipping per se. The tipping must be due to some kind of deformation that's occurred with the truck, with the crust. I don't know where Trump came from that. For instance, what's the belief of how the Rocky Mountains came to exist? Not glaciers. Scientists don't invoke the flood. I'm looking at the scientific explanations here. Yes, you have the Pacific plate subducting under the North American plate, causing the North American plate to squish in, and the crumple zone is where the Rocky Mountains are. And so that crumple zone is going to cause layers that were originally flat to tip. And in fact, it can cause them to tip over and be upside down. The second one, superposition, says the younger layers should be on top. Because if you have horizontal and you have sediment flow in, it's going to flow in on top, right? It's not going to flow in underneath. So you should have younger material on top. But once again, if things have been tipped back, if they get back to here, then you're going to have the younger ones actually underneath the older. And if it keeps going, you can have absolutely inverted layers. Not going to be common, but they can exist. Cross-cutting is another interesting one. Our first clicker question is going to be on cross-cutting, by the way. Cross-cutting says that if you have a crack, that the newer crack is going to cut the older rock. So if you have multiple cracks, multiple layers that have been filled in, you can determine the relative ages by which one is, newer. Now let's go back to a few more things. We have both relative and radiometric dating. Relative dating is using that theory of superposition that the younger is on top of the older. We get relative dates of this is younger and this is older. And so we would always say that the Cambrian is older than the Mississippian. that's just a relative dating. It doesn't say how many years ago the Cambrian was or how many years ago the Mississippian was, just that one's older than the other. That's relative dating. The relative dating method is pretty much agreed by everybody. The radiometric dating, it gives you an absolute age, and that's the one where creationists who stand by Usher's chronology say, no, that doesn't make sense. Or even the worldwide flood. How long ago is the worldwide flood according to using biblical reckoning? About 4,500 years ago. And scientists will tell you, if you look at geological features, there has not been a flood in the state of Arizona for at least 100,000 years. And so you have a contradiction there between the Bible's dating of the flood and the scientists' dating of the features in Arizona. So most scientists discount the idea of a worldwide flood, or specifically a worldwide flood that's happened recently. Okay, in the rocks, you have inclusions. Inclusions is a crack that's been filled in with younger rock. So you have older rock with a crack having younger rock in it. I'm going to not talk about the lateral continuity and just go down to faunal succession. Assuming superposition, I should be able to look in a younger layer, and what I find in that younger layer should be something that lived more recently. The fossils I find in an older layer should be things that lived longer in the past.
So which one is that one?
That's faunal succession.
No, wait, that's what?
That the fossils that I find in older layers were things that lived in an older time. Fossils I find in younger layers were things that lived in more recent time. And as you saw in lab, there are some types of fossils that are in many, many layers, and some types of fossils that are very specific to the layers they're in. So that means that there are some kinds of species that had a long time that they were living on the earth, and other ones that only existed for a short period of time. And so we can use those fossils that had a short period of time to get pretty accurate identifications of which relative layer are we in? How old is this layer? And that's something you did in the lab last week. So there are gaps in the rock record. Once again, you saw in the lab, I really liked that lab, okay? I think I've said this 3 or 4 times now. You saw that you can have gaps in the layers, and here's some examples of how they could occur. So you have layers that were formed, 5 layers shown there. Then you have something that causes crumpling. So you have, it's no longer flat. You have the inclines. And then you have something on the top that starts eroding. And so it starts eroding, and you'll notice that you have a new layer here, new material that's been deposited right there. Let me change it to a color that stands out better. New material that's been deposited there on top. And then you're going to have other places where material has been eroded away, so it's not as thick. Well, that keeps going, and you can get it so it's basically cut down like this. Okay, that's not where they did their cut. They did their cut more like that. And then you put new sediment layers on top because it's changed to being underwater again, and you fill in the layers, and then you come and you look at it and you find, well, you've got missing layers here. Right, there's 2 layers missing there. There's 1 layer missing here, or excuse me, no layers missing there. 1 layer missing here, and so you have missing layers because of the erosion that occurred in between. That was one of the 2 ways we talked about having missing layers. The other way we talked about having missing layers is it wasn't in an environment for layers to be put down, and that's actually what's going on right here. There's no layer above there because it was not in an environment for making a layer. It was on a high spot that's going to be eroded. Whereas here it was in a low spot and it was putting in new material. Okay, our first and only clicker question. No, I don't want to install software in the middle of class. 3 dikes, which are igneous intrusions. Igneous, melted rock. Intrusions, they're cutting through the old rock. Cut into a rock body. Which dike, you have the picture here, is the oldest and which is the youngest? Leslie was the first in.
Oh, no. Should I answer that?
I'm not judging your answer. I'm saying you're the first one in. Okay, everyone's answered. We had 1 for 1. All right. Instead of going to a student here, I am going to just explain it because we only have 13 minutes left. If we look at this, we see that A cuts B. If A cuts B, which one is newer? Which one's older?
He's older.
So B is older than A because the younger one cuts the older one. And then we look and we see that B cuts C. So C is older than B. So now we just put these in order. C is older than B is older than A. So C is the oldest and A is the youngest. So C is the oldest, then B, then A is the youngest was indeed the correct answer. So it wasn't a significant logical problem, but you had to think through just the basic principles. Radiometric dating. This is the last thing before we look at the different periods. Radiometric dating is the primary way that we see the ages of these layers, to put them in absolute numbers. And we can't use carbon-14 dating. Notice it says here the half-life is 5,760 years. That's what our textbook says. 5,730 years is what I usually see. The uncertainty on that number is something like 20 years, so 5,760 is just outside of that uncertainty I quoted. So we can't use carbon-14 dating to date things that are in the millions of years. It just won't work. So to date things in the millions of years, we have the 3 above are some of the primary ones that are used. Uranium decay. Uranium decay is a decay sequence. It's not just a single decay. Uranium decays to thorium. The thorium may undergo some betas and come back up to uranium again, or it may have a direct another alpha decay and go to radium. But you have, I think it's a total of 8 decays going from uranium to lead. The first decay is the longest one. It's the time limiting step. Everything else occurs with much shorter half-lives. And so as a practical rule, you could measure how much uranium, how much parent you is. You notice there's 2 different parents here. Uranium-238 and uranium-235. Uranium means it has 92 protons in the nucleus, and so those have different numbers of neutrons in the nucleus, and you see that the uranium-238 has a really long half-life. Uranium-235 has a much shorter half-life comparatively. Let us suppose we started with equal amounts of uranium-235 and 238. What would we have today? Will we have equal amounts of the 2 still? Which would we have more of? I'm looking at Dan because she answered correctly. We have more of the 238 because it's going to have a longer time before half of its decay. In fact, if we started with 50% uranium-238, 50% uranium-235, Right now, we've only gone through one half-life for the 238, so we have half of the uranium-238 that we started with the Earth. Whereas the uranium-235, if the Earth is 4.5 billion years old, we've gone through, what, 6.5 half-lives for the uranium-235? So 1/2 raised to the 6.5 power, that's somewhere about, let's say, 1/100th. So we should only have about 1/100th or of what we started with of the uranium-235 and 1/2 of the uranium-238. That actually comes pretty close to matching what we have, because it's about 2% uranium-235 and 98% uranium-238. I think it's more than 98% uranium-238, less than 2% uranium-235, but it's reasonably close to that. By the way, if you're going to make a bomb, only one of those makes a good bomb, and it's the uranium-235. Well, there's not much uranium-235 compared to uranium-238. So if you're going to make a bomb out of uranium, you have to enrich uranium-235. You have to find a way of separating the 235 from the 238. And that's what was done up in Richland, Washington. I used to work in the lab where that was, well, I worked in the government lab that's there now at the facility where they did that before dropping the bombs on Japan. A very inglorious event. Potassium-argon dating has a half-life of 1.3 billion years. That's actually a really useful one for dating rocks because argon is a noble gas. Not sure why I'm in that one now. Here. Argon is a noble gas. If you have molten rock, the argon gas should be able to escape. So you should be able to say, I say should, we know that it's not correct, should be able to say that the molten rock had no argon-40 in it. And so any argon-40 that's in my solid rock has to have been produced by the decay of potassium-40. Like I said, the fact is we know that's not correct. And scientists have found ways to go ahead and calibrate to try to find out how much they started with. Excuse me.
So
question.
The stable daughter product, is that after decays? Or?
Yes, okay. That's after decays. Okay, so let's look at a blow-up of our time scale. So here we have, notice this is not a linear time scale. Vertical height does not indicate how big the gap is. Precambrian time has the Hadean, Archean, and Proterozoic. Then we get to Phanerozoic. Phanerozoic is when we really have the life forms. We have Cambrian, first fossil plants. Ordovician, your first vertebrate fossils. The Silurian, your first insects. You can see there's reasons why these have the names. The first is something. The Devonian has your first amphibians. Carboniferous is broken into two pieces, Mississippian and Pennsylvanian. The Carboniferous are where you find lots of coal. And the Mississippian and the Pennsylvanian are, you find the coal in Mississippi is from the Mississippian. The coal in Pennsylvania is largely from the Pennsylvanian. Right? These are reasonable. The Permian gives us our first reptiles, and then we have the Mesozoic. Now, Paleozoic means the old. Mesozoic means the middle. And the middle here, the Mesozoic, that's dinosaur time. So you have the Triassic, the Jurassic, and the Cretaceous. Those are the time periods that are filled with dinosaurs. You said Jurassic has your first bird. And then the Cenozoic, that's the recent time. The Cenozoic is when you have the age of mammals. So dinosaurs dominate during the Mesozoic, mammals dominate during the Cenozoic. And then you see in the Cenozoic, we break it up into smaller epochs, the Paleocene, Eocene, whatever, Pleistocene, that's the Ice Age period, and Holocene, the present. So we're in the present, we're in the Holocene. Eons are your oldest. Eras, then periods. And so the work we did in lab was looking at the periods here in the Paleozoic. And then the epochs are the smallest region. So that is the way of dating, and these have dates with them. So when you say it's, well, let's just choose Jurassic. When you say it's Jurassic, you're saying, well, that's the layer that's above Triassic, younger than Triassic, but older than Cretaceous. And then looking at these numbers, you could say, oh, yes, the Jurassic is in that time period. So this does not show the break-off lines. We'll see those in the coming up slides, which I'm going to cover in theory in 4 minutes, in practice not so quickly. So I will finish this review of the time scales before I do the review for the exam. Precambrian time goes up to around 543 million years ago. Depends on which year's table you look at where they're going to put the dividing line. It's 90% of the Earth's history is Precambrian. And you do have some things there. You have lots of volcanism, lots of volcanoes. You have the little tiny bacteria things, cyanobacteria. Those are things like, you guys, okay, I asked this before. How many people had been to Yellowstone? I think it was just one, wasn't it? Must have been Ashton or Rachel. Well, in Yellowstone, you look in these, they have these pools that are super hot. Just a year or two ago, some guy was walking out there. There's things say don't walk here. He was walking out there, fell in, and got cooked. Because they're super hot. They will kill you. That's why you're not supposed to be out there. But they have pretty colors. And those pretty colors are caused by living things that are living in that scalding water, cyanobacteria. And the cyanobacteria can only live in very specific temperature ranges, it turns out. Well, those things are really ancient in origin. We find cyanobacteria going all the way back. So cyanobacteria exists today and existed prior to 543 million years ago. Soft-bodied organisms. Soft-bodied organisms are pretty hard to preserve because you squish them and they not much there. You had a different atmosphere. The oceans were different. The beginning of plates is all Precambrian. Fossils you see, this is your classic trilobite. The trilobite, they look like glorified cockroaches. They lived in oceans. You know, I see that and I tend to think it's a glorified cockroach. It must live on anything. But they lived in oceans. I've been up there to the Burgess Shale where they have trilobite. It's actually really cool. Stromatolites. Stromatolites are a thing that still exists today. It's a bacteria. I'm going to end on this slide. In the Precambrian time, we believe that there were 3 atmospheres for Earth. The first atmosphere is the atmosphere of when the Earth was formed. When the Earth was formed, we had hydrogen and helium, the primary elements. And so the first atmosphere would have been pretty much hydrogen and helium. But the Earth is not massive enough to hold hydrogen and helium. The speeds at room temperature of hydrogen and helium are faster than the Earth can hold on to, so they can escape. So the hydrogen and helium atmosphere was lost, replaced by a secondary atmosphere that is the gases that came out of hot rocks. The gases that came out of hot rocks, you have things like carbon dioxide, water, methane. Well, those have largely been taken out of the atmosphere. And now we have a third atmosphere, probably came from comets, that is primarily nitrogen and oxygen. The atmosphere we have right now is about 79% nitrogen and about 21% oxygen. Other things are just trace amounts. And that's where I'm going to stop today. I will quickly go through the eras Paleozoic, Mesozoic, and Cenozoic, and then review on Wednesday.